Welcome back after the lunch break to the NanoSafety cluster training day attached to the NanoSafe digital conference. Let's have a quick view on the schedule. So we are now going to have a 1 hour, quite intense training session, hands-on, interactive as possible, of the NanoSolvit tools for assessment of human and environmental exposure to nanomaterials by the team of Andreas, who is the coordinator of the project. So at first, Nikos Chimerios is going to present, and he does this very hands-on via screen sharing into the tool, human exposure assessment of nanomaterials. And in the second part of the session, we're going to have Samuel Harrison and Pantelis Karatsas, who are going to show us environmental assessments. And we're going, in both of these tools, look into the tools to really get a clue and understand how they're working. There's quite an extensive list of things that we have on the dashboard, so please take note of the dashboard on top. If you follow the red, click the red button and follow the link, and you come to the NanoCommons powered dashboard for this event. And there you find lots of links that you can get access to the tools that are shown here. You can also see and find examples there and find tutorials and further information. And moreover, we have also installed 2 parallel Zoom meetings, Zoom sessions, where we have some experts waiting for you to assist you in some of the things that we run through. So you can in parallel work on the tools. And when you encounter problems, get there into the Zooms. The links are in the dashboard to get support or can clarify any other questions. There is Andreas and Georgia are sitting in one of the breakout sessions in the Zoom link, and Andreas Zumanis is sitting in the other one. So you are very, very encouraged to take advantage of this possibility. I would also like to announce once again, if you are interested in this education and training, we are going to, of course, extend on that. Stay tuned to our working group A on education, training, and communication. Go to the website. I will post the link again and sign in the mailing list. With this, I would like to hand over to Nikos, who by sharing his screen is going to take over and give us insight into the human assessment exposure. Nikos, please.
Okay, thank you very much, Martin. First of all, sorry, it seems that there's something wrong with my camera and I cannot share my video. I do apologize about that. Let me start first with a short introduction of the tools that we are going to see together. Both concern the human exposures in nanomaterials, and we have developed 2 tools, actually, one which is based on a multi-box aerosol model, and the other is a dose estimator for human lungs of the nanomaterials. So first, concerning the human exposure assessment, we have developed an application in order to evaluate the human exposure in nanomaterials. So we want to evaluate actually the concentration of nanomaterials in indoor environments. In order to do that, we have the basic, let's say, unit that we have is a room, which we are partitioned to different areas. The basic, one of the basic areas are the near field, or the NF area, which is the location where the source generator exists. The source is where the nanomaterials comes into the environment. The other all areas are called far field or FFs, and we can have multiple areas. Every area inside the room must be embedded to the larger area, and it can be cuboid or cylindrical. Here, on your right, you can see a simple example where we have a room, and we have partitioned it into an NF, which is inside an FF1 and inside an FF2 areas. So we will see many examples of how to construct such sketches of rooms. Now, concerning the input to the application, we need the diameters distribution of the nanomaterials that characterize the source, that we call the bins, as you will see. And for now on, we can treat many nanomaterials, such as black toner and titanium dioxide. Of course, we have the possibility to create our distribution of bins in the application. For the output, what we will get is the concentration of the nanomaterials per bin per box. Now, this is for the multi-box aerosol model. For the other model, the lung exposure model, we want to have an estimation of the dose of nanomaterials in humans. So in the input, again, we need the diameter distribution of the nanomaterials, but and if you see that correlated with the aerosol model, we need the concentration of nanomaterials in different areas of the room that we have partitioned. And the output is the deposited dose in these regions of human body. So, concerning the software applications, the multi-box model and the lung exposure model are both developed in Java. The multi-box model uses an Apache Common Math 3 dormant prints algorithm for the time integrations, which make it very efficient. And both applications use ZK framework. Here are the two links that we're going to use. So this is in general a very quick presentation of what we're going to see and interact with, hopefully. So here we have uploaded several documents that we are going to use today that you have access. You can find them here in this link in the NanoSafe dashboard. You can see that we have two tutorials. These are generic tutorials in a sense that they give you instructions of how to use the software in a more generic way. But also we have gathered the examples that we're going to use today. These are exactly what we are going to do. So in case that you want to do something on your own or we don't have many time to do so, you can follow these instructions in order to repeat it. For both applications, the links can be seen here for the aerosol and for the lungs exposure. Let me close my. So I press here in order for aerosol to open, and this is the aerosol model for the estimation of the concentration of the nanomaterials. I would strongly suggest, if you want to join me and also try to repeat what I am doing, I will do it rather slow in order to be able to follow me. And of course, we can discuss as long as we work together. So the first thing that you see, it's the computational domain. Here is where we have to partition the room to the areas that I mentioned, the near field, the NF, and the FF. So in a simulation, we can have, of course, one room. one NF, because there we assume that we have only one source inside this NF, but we can have multiple FFs. For the first example, we are going to use only one FF. So here we can see the areas, the schemas, which can be cuboid or cylindrical. Here is the starting point, which is if we use cuboid areas, it is the lower left corner. But if we use cylindrical, it's the center of the circle. Here we define the schema dimensions. This is actually the dimensions of the area. And this is our flows which connect the boxes, the areas among them, and to and from the environment. So flow to next area is the communication between two areas. And from inlet, it's a flow that comes from the environment inside the different areas. And flow to exhaust is the flow going out from the box, from the area to the environment. So for our first example, I'm going to use here a starting point of 1 for the NF and a schema dimension of 2. For the flow to next area, to FF1 actually, I will put 10. And for the FF1, I'm going to put it as to be the entire room. And this is important because when, in order to have deposition inside our model, to enable the deposition, the sides of the area, for example, the FF1, must coincide with the side walls of the room. So, from practically speaking, if I do this, then you see here that this side of the wall does not match the sides of the wall of the room. So, in this wall, we are not going to have deposition. So I'll add here, so we take into account that in every wall of the room, we will include deposition. And I put here again 10 for the flow to next area, which is actually the NF. This is the other way around. And for the flow to exhaust, I will put 5. And this concludes the computational domain. For our second continuing, we need to have a scenario description, which actually is the material that, the nanomaterial that we are going to use to our simulation. In this first example, I'm going to use black toner, although we have plenty of materials to use. And for the simulation input, I'm going to use a value of 300 seconds. This is our modeling time that we're going to solve to integrate the equations. And for the time of source being active, I will put 50, which means that for the first 50 seconds of the modeling time, the source will be active. For the repetitions, I will put 1. I will include coagulation and deposition in our computations, and I will not change the physical parameters. And I will press simulate. So it's rather fast, as you can see. So here are the results. Which first we have to select the area that we want to see the concentration. For example, I can use for this problem NF, and then I can use the bin. The bin is the concentration, is actually the diameter, the specific diameter of the nanomaterial. And here you can see directly how the concentration of the nanomaterial in the NF area elapses with time. And you see here that for the 51st seconds, as we put here, the source is active, and then it when the source closes, then the concentration drops. And we can see here also for the FF1 area that as it first increases, and then we have a small drop in larger times. Of course, if I want, I can download our example in a CSV format for in order to further manipulate them. Give me a moment to open my cell, and I will give you an idea how is this file structured. Okay, so first of all, so we have the input information, which is summarized here. This is because in general, we want to have an integrate all the information that we have used. So this is the input that we have used in order to generate the output, where the output, as you can see here, this is for the near field area, the NF area. Here are the time steps, and here are the concentration of will be active as we will put the simulation. So we will have one from 0 to 50 seconds, and then from 300 to 350 seconds, the source will be active. And this will be clear in our results. So here, if I could put an F area and bin 1, here, okay, you can see here that we have a jump from the first source until 50 seconds, then it drops again, and then it goes up again because the source is active again in 300 seconds. And the overall second. Now, for time, in our other example, we can use again the same computational domain, but instead of black toner, we will use the titanium oxide. You see here, this plot, this graph here is the diameter distribution, which actually, these are the bins, and this is the emission rate that we use in our calculation. So if I go here again, I will put 1, and I will put simulate. Sorry. Okay, it did it. So the execution time of the code depends highly on the number of bins that we have. Titanium dioxide has less bins, has actually 14 bins, half of the black toner. That's why the simulation was faster. And again, I can see the concentration in the different areas. Sorry about that. Here, for that bin, the initial concentration is 0. That's why I get 0. So here you can see again the concentration over time. Now, to other functionalities, I will go back again. Okay, and instead of using cuboid for NF, I'm going to use cylindrical. So the radius, now it sends here, and you can see the radius. Of course, the radius is 0. That's why it shows nothing here and only a line here. I will put it to 2. And hopefully you will see. Okay, didn't do it. Okay, we had a small latency. So here you can see that I replaced the cuboid for the NF to a cylindrical one. And I will use black toner again. And I will go to simulate. Okay, and now again, I can see my results. Okay, here you see that there is a more sharp rate here compared to the cuboid one. And for my final example on the aerosol application, I'm going to use two FF areas, all cuboids. So I'm going to go here and I will select 2. You see that these were updated. Now we have FF1 and FF2. I will put here cuboid and 2, and here, sorry, and here also cuboid. I will use this input for the NF, so it's 1, 1, 1, and for the dimensions is 2 by 2 by 2. I will put here 0.5, 0.5, and 0.5, and I will use a length of 3, 3, and 3. And I will put a flow to the next area of 10 and a flow to exhaust of 5. And again, my last region, my last area, sorry, it's which is FF2, it will be 4, 4, 4, and again 10 and 5. So I have constructed 3 areas now, for which I'm going to compute the concentrations. I will use again black toner, and I just have to press simulate and wait until I get my results. So now here in the area, you have NF, FF1, FF2, all the areas that we have. I will select all, and for the bin, I will select bin 1. And now you can see here how the concentration evolves over time for our different areas in the different bits. So I don't know if you have any questions about this model, because I'm going to proceed to the lung exposure model, or if you want to gather all the questions after the presentation. Okay.
Yeah, at the moment, there are no questions in the chat box, but I encourage people, put them anytime you want, and we're going to take care that they are going to be answered whenever possible. I put them on display. Thank you.
Okay, excellent. Thank you. Thank you very much. Now, for our other model, for our other application, we have created this lung exposure dose calculator. This is something that we are working on, and some things will be a little bit different. So here, what we want to do is based on the diameter distribution of the nanomaterials. We want to, and the initial concentration, the final concentration of the nanomaterials, we want to estimate the dose in humans. In order to do such thing, we have three methods to do that. One is theoretical, the other is called template, the other from aerosol. I'm going to show you examples from every one of them. Of course, everything is gathered again in the drive link that we have sent you. In the theoretical case, we want to load a DP distribution and to have an estimation of the concentration of the nanomaterial. In order to have an idea of how this DP distribution looks like, we have this box here, which is a DP distribution sample. And if you press it and open it, you will see that it's just a plain file with the values of the different diameters of the nanomaterial. And this is what I'm going to use. So I'm going to use the DP distribution that I just downloaded. This is a very, very simple case where you have a straight line. For the concentration of the nanomaterial, I'm going to use a value of 20. For the exposure duration, a value of 100. For the respired volume rate, a value of 10. And for the density, a value of 100. And I will press the calculate dose. And here, as you can see, I have the calculated dose in these different regions of human body in milligrams. Of course, I can download also the doses for further. This is the simplest case, the theoretical one. We have also the template case. In this case, we have again to provide a D distribution, but we also have to provide a concentration per bin of the nanomaterial. Again, we have a button which you can download the concentration sample. I download it, and as you can see, again, it's just a simple file with a concentration per bin. So if I load again the DP distribution and the concentration per bin. So I will use the same values as here, and I will press calculate dose. And okay, we have again our doses in milligrams. So as you understand, we need, in order for the lung exposure model to work, we need the distribution, the diameter distribution of the nanomaterial and the concentration of the nanomaterial per bin. The nanomaterial's concentration per bin is calculated by the multibox aerosol application that we just saw. So what we have done is that we have connected these two applications. So this is what is the method from aerosol does. So here, instead of providing any information, I compute it or I take them right away from the aerosol application. So if I press aerosol configuration, it pops up the GUI of aerosol. For this problem here, I will use a value of 111 for the FF, 2 by 2 by 2, and 10. And I will use for FF1 a value of 4 by 4 by 4, again 10 and 5. I will use black toner, and I will left here the default, and I will press simulate. So when aerosol finishes, then it loads up the results. So here you can see the diameters distribution for the black toner that I've used, and this is the final concentration per bin, per nanometers diameter that was calculated by aerosol. And these are the different regions of the boxes as I define it in aerosol. So here, the near field, the NF area is highlighted because this is what we have selected here. But if I want, I can select FF1, the other region. As you see, it was gray out. You will see that the concentration also updated. So I'm going to use an F here. I will leave this values here, and I will put calculate dose, and I have an estimation of the dose in the various regions of human. So this is what I had to say. I don't know if you have any questions or you want to see something together or do another example.
So we have actually one question in the chat, which I put on display if you look in the display. It regards to clearance actually in the lung. So quite an interesting and important issue. How much is this? Is this relevant clearance or not?
Actually, it's for in the lung exposure, we take into account the entire time of the exposure. So if we put in aerosol 600 seconds, then we take the sum of the concentration per bin. That is what we use in order to compute the lung, the dose.
And the question was also whether one can combine different concentrations of repeated exposures.
As it is now, no. Unfortunately, no. But I think we will work on that because it seems it is a very useful functionality.
I do still see that Rosalia is still typing. Maybe there is a question also coming up very soon. Yes, I put it on display.
Yes, thank you.
Translation to in vitro doses.
I don't know about that. I cannot answer.
In the morning when Langtran was presenting, very interesting and important topic, yes.
I have to get back to you about that, unfortunately.
Okay.
I see Andreas is writing something. Probably he has the answer. Okay, yes.
Well, there are a couple of approaches, I guess, pursued currently. Langtran was also mentioning them in the morning. And I guess this is relevant. This is something that, of course, hits into other projects too. We have noticed that. So we have already Samuel Harrison waiting to now drag this further to environmental exposure.
Okay, let
me thank you once again.
I thank you.
Nikos.
Yes, can you hear me?
Yes.
Okay, great. So thank you from my part.
So, Sam,
hello.
the stage is yours.
Thank you very much. Let me just check that I can move slides, which I can, so that's good. Yeah, thanks. So I'm going to now introduce the environmental exposure side of the NanoSolve platform and what we're doing with regards to incorporating an environmental exposure model into the NanoSolve cloud platform. So this is going to be a two-part presentation. I'm going to kick off by introducing the model itself, which is the nanophase model. And then I will pass you over to Pantelis, who will give a demonstration of the model in action in the NanoSolve platform. So I apologize, the first part of the presentation, which is me, is not that interactive. I'm just going to give a presentation, but it gives some important information about the model. So I thought I'd start with kind of reflecting on the past decade or so of nanomaterial exposure modeling, starting with, well, that's not me moving the slides. There we go. We have a rogue person moving the slides. Starting with why do we need to model nanomaterials? Why do we need nano-specific models to begin with? And why can't we just use conventional chemical models that already existed and make them adaptable and nano-specific? And this all comes down to the fact that nanomaterials, they can form thermodynamically unstable suspensions in the environment, such as heteroaggregates to environmental particles, such as suspended particulate matter. And this means we can't use equilibrium chemistry, and we need to make nano-specific models and tools to be able to deal with this. And accordingly, over the past decade or so, there's been a plethora of different nanomaterial exposure models created of a variety of different shapes and sizes. So we have models of, we have multimedia models, that box type models that give you spatially average distributions in different environmental compartments. And you have models that give spatial and or temporal resolution, usually just in one compartment. But the thing that was really missing from this was a model that offered both spatial and temporal resolution over multiple environmental compartments. And this was the gap that the NanoPhase project, which ended at the end of last year, this is the gap that the NanoPhase project aimed to plug with the so-called NanoPhase, nanomaterial fate and speciation in the environment model. So as a quick introduction, the nanophase model, so it's a spatiotemporal model of nanomaterial fate, speciation, and biouptake in the environment. And it's spatial, so it represents a geographical region by splitting it up into a number of grid cells. And each of these grid cells can have compartments representing the soil profiles and soil layers, and surface waters, rivers and estuaries in this example. And these surface waters can have bed sediments. And so I thought this is a slightly complex slide, but I'm going to come back to this later because it's quite important as to how we get such a complex model into the NanoSolve cloud platform. But I thought I'd just reflect on what such a complex spatiotemporal model means in terms of the data that are required to run it. And well, the overall picture is that the data required to run it are quite complex. So we have all sorts of different data, meteorological data, land use, soil properties, topography. And a lot of this data itself is spatial and temporal. Some of this needs to be passed through a hydrological model to give us hydrological flows. And then obviously we need information about the nanomaterial itself. So the nanomaterial's phys-chem properties, and how and where and how much of it is released to the environment. And so the general picture here is that such a complicated set of input data generally requires some form of expertise to run the model. And what that means in practice is that often models of this type of complexity are only really ever run by the people that create them. So just to wind back a bit and just to give you a bit of an example of some of the outputs from the model, I'm just going to show you some results for this scenario here, which is running the model for the Thames catchment in the UK using a grid resolution of 5 by 5 kilometres for the years 2000 to 2020 and for nano-titanium dioxide. And this scenario here, this is based on modelled releases. So they're quite realistic releases, spatiotemporal releases of nanomaterials to the environment. And so these are the kinds of questions we can begin to answer with this type of model. So here, this graph on the right, I'm just giving you an overview of the total mass of nanotitanium in the entire catchment, split up by environmental compartments, so soil, sediment and surface water. And then that graph at the top there, that's just giving you the emissions trend, so the masses per meter squared of nanomaterials emitted, just to give you an idea of how the emissions are increasing over time from 2000 to 2020. And the main picture here is that soil very much acts as a sink, and the main term driver to the dynamics in soil are these exponentially increasing emissions. And just to demonstrate that stuff is happening in the other compartments, this is the same graph but logged, and you can kind of see that in waters and in sediments, nanomaterials are increasing in mass over time, but not at as high a rate as the soil compartment. So it's a spatial model, which means that we can produce maps, we can produce spatial distributions of nanomaterial concentrations. And this heat map here is a map of the Thames catchment, and each of the grid cells represents the concentration of nano-titanium dioxide in soil at the end of 2020, so at the end of that 20-year model run. And the colour of the grid cell represents the concentration, and the more yellow the grid cell, the higher the concentration. And so you can see here clearly that the urban areas around London specifically have lower concentrations of nanomaterials and soils, and the areas outside, the more rural areas, they have higher concentrations. And this is down to where nanomaterials are emitted to the environment. So the main way which titanium dioxide gets into soils is through the application of sewage sludge, which obviously only happens on agricultural land in rural areas. And so we can say that the main determinant of the spatial distribution of nanomaterial in soils is land use. So soil isn't that dynamically interesting in terms of nanomaterials. So I thought I'd just reflect on a slightly more dynamically interesting compartment, which is surface waters. And this example here, I've picked out two reaches, a river reach and an estuary reach, that are kind of representative of the whole catchment, just to give you an idea of how nanomaterial concentrations change in these compartments over time. And again, I've just given you the emissions trend at the top there to give you an idea of how nanomaterials are being released. So the main conclusion here is that the main driver, particularly in rivers, to nanomaterial concentration is the hydrological flows, rather than the emissions trend, which is why you have these big peaks, which coincide with the summer months when the river flows are low. Estuary is a slightly different picture. Obviously, it's quite noisy, and you do have these peaks and troughs, but that you can kind of see that there is a bit more of a trend in line with the emissions trend there. And that's down to the fact that, well, estuaries waters can go upstream and downstream, and this upstream flow acts to dampen the net downstream flow of nanomaterials, and it basically traps them in place a bit, which it gives them a bit more of an opportunity to build up. Hence, you're seeing them acting slightly more as a sink. Okay, so just to reflect on this, how this type of model is generally used and how useful it is for regulation. So as I've already said, it's a complex model, which means that it's not easy to use. It needs experts to use. And so you'd only really ever use this in a regulatory context as a last step. So if you'd already gone through some kind of tier approach where you had done some simple calculations to determine the risk to the environment, and if those calculations came out saying, oh, actually there might be a risk, and those calculations would be as conservative as possible. So that's on this graph here, that's the lower tier. You then might move on to a simpler model like SimpleBox for Nano, which again is conservative by nature, but is a bit more realistic than your simple back of the envelope calculations. And then if this intermediate tier model, SimpleBox for Nano as an example, indicated that there might be risk, then you might consider moving on to a higher tier model, a complex model like the nanophase model, to give you as realistic a picture as possible of how nanomaterials are distributed in the environment. And so this kind of made us ask the question that motivates a lot of this work in incorporating the nanophase model into the NanoSolve cloud platform, which is, well, what if we can simplify the model inputs such that we can create a GUI that makes this complex model as accessible as possible to non-modelers, regulators, industry. So I just want to quickly come back to this slide. So when we're thinking about how to do this, we kind of realize that, well, actually, a lot of the complicated information, the spatiotemporal information, can be broken off into what we call a geographical scenario. It's stuff that represents the geographical region that you're modeling, like the hydrology, the soil. And actually, we can fix that. So we can give users a geographical region in which they're able to model. And that means we can abstract away a lot of the complexity of the model. And so this means that the only things that the users need to define then are the characteristics of the nanomaterial itself and their emissions to the environment. And in fact, we can abstract away the phys-chem properties of the nanomaterials by giving them a predefined list of nanomaterials that they're able to model. And then the only thing that they're left to have to do then is to define how and where and how much nanomaterials are emitted to this fixed geographical region. And then I've focused a lot on the data input here, but just to say also, I mean, the model outputs either netCDF or CSV files, which are not very user-friendly, but obviously a great advantage of having a user interface is that you can then visualize the outputs and as user-friendly a way as possible. And hopefully that set the floor nicely for Pantelis now, who I'll hand over to give you a demonstration of how that works in practice. Over to you.
Perfect. Thank you, Sam. I hope now that you are seeing my screen. You can find the available links for the application at the training day dashboard that is created for this meeting by pressing at the NanoPhase Cloud NanoSolve EU. Someone will be guided to the landing page of the application. The first thing someone has to do is to log in to the application or register if not already a user of the tools that we are creating. So after the login, the page redirects the user to the catchment of themes that it is already modeled and integrated into the application. Each user has its own list of emissions, scenarios, simulations that can be shown up on the map, as we will show in a while. And some other actions that can be done upon the map is entering a polygon, a point, zoom in, zoom out to the map, and change to the theme that he likes more and have a better representation of the results. So we are here at the themes catchment. The first thing is for someone is to add emissions upon the map, as Sam mentioned earlier. So one can add an aerial emission by creating a polygon where the emission is happening. And when the polygon is closed, the data of the emission are entered. you have to enter the nanomaterial, which is the dioxide of titanium. Let's say that this specific emission happens on soil with pristine form, and let's say that the emission consists of 1 kilogram per meter square per year. So, as this one emission could already be an input for a simulation, but a more realistic scenario would probably consist of more than one emissions. So, let's add, for example, another emission, a point emission. Again, by adding all the required values. And again, 1 kilogram per meter per year, save. So right now we have two emissions on the map, and we can further continue adding more emissions if needed in order to create a scenario. When emissions are shown on the map, we have a button here which let us store these emissions in a scenario. And when these emissions are stored as a scenario, the button changes from save to run. And this is available whenever a scenario is shown upon the map. Let me show again something. I can go upon the emission and change, remove from the map and do whatever I want. Then again, I have one emission which is not stored in a scenario, so I can save again a scenario. Now I don't have anything, so I don't have a save. I have the scenario, a personal scenario list that the user have created. So then again, I can use again that scenario to run the simulation. So when the scenario is presented upon the screen, then I can go on and create a simulation. I just add the simulation name, the simulation description that I would like to have, and I'm choosing the start date for the simulation. The simulation outputs will be 365 days of simulation upon the specific catchment. So let's say that the simulation will start at the 1st of November. Now I have the start date of the simulation, and I can continue with and I can press the run button, which will create me a simulation. After that, the simulation will be available and running, nanophase simulation, as we see here. And I can see the simulation. It takes a lot of time for all the data to be crunched and create a useful schema, a JSON schema that we need in order for the GUI to be able to render the simulation outputs, also to be stored on databases and get all the results through the API. So someone should have a little patience in order to see to start seeing some models, some outputs. In order for the demonstration, we have created a simulation, and every simulation has its own URL. So this URL is also shared with you through the dashboard, and so by clicking one can see the outputs of a simulation. So the outputs are grouped into three categories. One can show the outputs for the water, and I'm pressing water and I'm choosing now that I would like to see the water, and I would choose then the output day. By clicking on this line here, I choose now the 31st day of the simulation. On the map now I have rendered some points, and when I click upon a point, I can see all the simulation outputs. I see the time, which is the 31 day, a date time, some features that depends upon the output, and then I have all the values that I need in order to get further understanding about the simulation that we have created. So the first thing that we want to notice upon that, this is not the most user-friendly output rendering, but we have the values needed in order to continue further down with further integration with kinetic models and other hazard models by using these values as input to these models. This version of the application is a beta version, and right now we are working on better interpretation and rendering of the models, and the final output will be something like that, where a more reactive rendering will be available for the end user in order to see the concentration of the nanomaterials due to the simulation and upon the whole catchment that it is available right now. The same applies if I choose a soil output, and again I can see the values that concern the soil outputs. Also for the simulation, I can see the simulation's emission, and I can click upon them and see from where everything started. Right now it is this little dot behind the bigger dot of the layer that renders for us all the outputs. So basically, this is the application state right now, and more features will be available and make this application more easy for the end user to use and get a better understanding of how the nanomaterials will be distributed in catchments around the world. We hope that this application will be extended and integrate more catchments around the world. And that's basically what we have to show you until now.